Okay, let's get started. Good morning. Hope you all had a good spring break. It's not a good thing when you have to come back from spring break on the day that the time shifted too. So I see the most of this building looks very sleepy for now, right? At least it looks like spring is going to be here soon. So do you have any questions about what we covered on memory management? How many of you thought about or started the homework project over the break? If you haven't, look at that one. So if you look at the project, there's two components, right? One which collects the data about a running application, and another one to build a simulator, right? At least first look at the running the program, because that ought to be straightforward. But that'll get you kind of thinking about what kind of program you have to work on, right? And again, for this project, some of you may realize that it's not all that hard. The intention here is not to make you do lots of programs, so it's okay if you don't have to write pages and pages of code, right? You have to understand what you're trying to do, and not necessarily on the coding part. So this is not a programming class, and I'm not trying to make you write lots of programs, right? But you need to think about what is really happening, right? And I really like that program because it tells you, it gives you a trace of all the instructions that your program goes through. So you'll see that even a simple program goes through a whole bunch of instructions, right? So let's going back to the memory management. I hate to kind of split the module in the middle of a spring break. So hopefully people still remember what we talked about before we left, right? So one of the things we were talking about was you had to come online fairly soon because the next exam is on Friday, right? So one of the things we saw was like the different programs, when you write the C program or what have you, has different segments that you ask, right? So you ask the operating system for a program area called text, read only or read write segments, right? And we were trying to figure out how that maps into what the operating system, like where the operating system gets involved, right? And we're looking at sort of like different techniques and sort of they build up to what regular operating systems manipulate. The first one is the notion of a logical versus physical address. And this is pretty powerful because that lets you, as a programmer, see one address space and operating system to move it anywhere it wants, right? So your program can still refer to memory as 1000, whereas the physical address may be different, right? So your CPU always sees the logical address, your program always sees the logical address, and through some translation, you go from your logical address to the physical address. And we'll see how one such translation is done in the next few slides. But essentially, for this to happen, you need some hardware support, because every address will now have to go through this addition operation. So unless you have hardware support, your program will be extremely slow because everything, you have to do one more addition. So if you have instructions with, let's say, 3 memory operators, you're going to take 6 times as much speed. So this is only possible if you have a unit called MMU, which most modern machines will have, right? So some of the things we see in this chapter depends on hardware support, because this involves every instruction of your program. So unless you get hardware support, your program is going to be slow, because either hardware has to be there or the operating system has to translate every single instructions, and doing it in software is very slow, right? So the next notion is the notion of swapping. Essentially, you move if the operating system knows that a particular memory is not going to be used, it could potentially move it to a hard disk or somewhere else, and use that memory for something else. So if you are not using some memory, it can be moved to the hard disk, bring something else so you can keep running, right? And you can sort of see where you go with this. When you have multiple processes and you want to bring one in and context switch the one out, that's a good point to move so if a process is being context switched, you can move all the memories it was using off to the hard disk, right? Which is a good thing because now you get more memory, seemingly get more memory. It's a bad thing because now a context switch is more expensive, right? In the last modules, we looked at context switch where you have to change the CPU context. Now you're also potentially moving stuff to hard disk. So if you context switch a new process in, right, you have to restore all the CPU state, and now you have to also restore all the memory state, bringing it from the hard disk, right? And then we'll see a little bit how bad or good this could get, right? So remember the previous model, because we're not completely out of it, because it's still the same operating system. So some of these things can happen when you do a context switch. And then the issue of how to allocate this memory chunks to you, right? You can either allocate it as contiguous, you can have the whole program as one contiguous section, or you can give it in non-contiguous sections, right? Meaning your text could be in one area, your program read-only data could be in another area, something else could be in another area. You as a programmer won't know how these things are laid out, because if you write a good program, you should not access memory that you didn't claim to use. If you didn't, then you'll notice some of these things as segmentation fault, right? And one way to enforce that is through having base and limit registers, which basically say, this segment I'm allocating to you, and this segment, this is the base and limit, which means that it starts here, it ends here. If you try to access anything beyond this, then you should get some kind of error. And those again are done by your hardware. So before you load a program, you have to say, I'm going to give you this segment, this is the base, this is the end, and this is how you should do the translation, right? So you need to have the logical to physical translation and the two base registers, right? And then you let it go. And the other issue we looked at was, how do you allocate these things? So if you have large memory, you kind of allocate it, as a, so you either get into a notion of external fragmentation or internal fragmentation. External fragmentation is when you do allocation, and you have a little bit area left which you can't use for anything else, right? So that's sort of where we left off, right? To make sure that you understand what's all the stuff, so this is, let's say you have a process which has 3 of these memory segments, right? So if you're going to allocate it in a contiguous segment within this, in whatever size you wanted, right? The first problem was to try to figure out if this is the physical memory, and this is 1, 2, and 3, how to fit this into here, right? So you may set up as 1 and 3 and then 2, right? And may turn out this is too small, so you don't get to use for anybody else. So this becomes the external fragment, right? The other issue is, the limit and base register means that when you load this program, somehow you have to tell the memory management unit that there is this address and this address, right? This address and this address and this address and this address, right? So when a process gets context switched in, you have to tell the MMU that you as a process can only access from here to here, here to here, and here to here. You can't use anything else, right? And you have to do the translation from logical to physical, logical to physical, logical to physical. Did that make sense? Every time you so all this are per process, right? So when you load a new process, you cannot let the process run till the memory management hardware knows about the logical to physical translation and all these limit registers, right? Because if you don't, your program can access this area and you won't know the difference. If you don't, then if it tries to access a logical address, it may not know what translation to physical address, and you get wrong values, right? Does that make sense? So you have to load all the stuff before your process runs. So, and to make matters even worse, this might have been swapped out. So you'll have to swap it back in, load these registers to the MMU before you start running. So when you do a context switch, I may have to store some memory pages into disk. I may have to bring something back, load all these MMU registers, and then start going, right? And turns out that the MMU, you don't want it to be too complicated because then it becomes more expensive. You don't want it to be as big as your CPU or expensive as your CPU. So rather than loading a whole bunch of these, right, we are going to do optimization which will cause internal fragmentation but makes life simpler, right? Essentially, here you're saying, I need to know which ones are allocated to my segment, which is the physical to logical translation, and I need to know the base registers, right? I'm going to solve it by saying, I'm going to allocate it to you in fixed chunks, Let's call them pages, right? So that way, I'm going to give you a page. You get the whole page. So I don't have to give this base and limit because the whole page is to you. If you access anything which is not in your page, then I'm going to create a fault. Otherwise, there's no fault. And I'm going to, by the page number, I can do this translation also very easy, right? And then we'll see how we do that in the next slide. But do you understand why we want to do that? We don't want to allocate into small chunks because nobody prevents this program from asking for another little small chunk, right? The more segments you ask, that means all of these segments have to be given to the hardware, right? So either you have to limit how many segments you can give here based on what the MMU can do, right? Which makes the program not so flexible. So instead of doing that, we can do a simpler way. And what we do that is we only allocate it in one fixed size, and we'll call that page, which means that this will have to be allocated maybe as number of, let's say, three pages. This may have to be allocated by, let's say, 2 pages, right? You only ask for this much, so this is going to be wasted because I'm only going to do fixed size. This only I'm going to give you like this big. You only ask for this much, so this is going to be wasted, right? That's an internal fragment. So you asked for this much. I'm going to give you this much. You can access it if you want, right? I'm not going to be able to protect you because all I'm going to say is if I give you a page, you're free to allocate that page, whether you wanted the whole page or not. You're not free to modify anything here because I'll catch that. I can get rid of this limit and base register by going with this one model. Allocation becomes a lot more easier. I don't have to do the best fit, worst fit, and all those things we talked about because all the pages are the same size. So if you want memory, I can only give you in multiples of pages. So I don't have to figure out whether it fits or not. I just find the next free one and I'm done, right? So page allocation becomes easier, much faster, right? And I don't have to worry about this limit registers. So everything becomes nice, and most of the problems are solved, and that's what we will do, right? So what's the flip side of that? Why would you still prefer something like this, where you have variable size segments? So if you go with the fixed size segment, you don't have to worry about external fragmentation. You don't have to worry about this base and base registers, right? What's the other side? Is there a reason why you would still like a big chunk? Why I'm asking is this is what we'll do for the file system too. When you go to the hard disk and file system, they also try to do the same thing. They also try to have same size block to solve the exact same problem, right? And there also they have to worry about whether we should go with a single same size or allocate different sizes, right? And traditionally we go with the same size. But that doesn't mean that the discussion is over. People still worry about whether we should go the other way or not, right? Can you think of a worst case for this scheme where we have pages of constant size? Yes?
They would only ask for like the minimum. Every process only asks for the minimal amount so that like everything's wasted.
You create lots of internal fragmentation, right? This is the internal. So if you ask for this much, you get this. You get wasted this, right? That's called internal fragment, right? So you could potentially have lots of internal fragmentation depending on how you ask the stuff, right? So if you ask 1 byte, if you keep asking 1 byte segments, then if I have to allocate it, say, as 8K pages, then essentially you waste the rest of the stuff, right? So in the worst case, if you keep asking lots of small memory chunks, right, you will waste the rest of the stuff, right? And this is the reason why when you do a malloc, right, when you do a malloc system call in C, right, it can't let you directly call the operating system, right? Because when you do malloc, you're asking for some memory chunk, right? So if you ask for 1, you're asking for 1 byte, right? And if you're asking for 1 byte, if you're going with the paged model, then I have to give you 1 page, right? if you ask the operating system directly. So if you implemented malloc in the operating system, which it does, you ask for 1 byte, it has to give you whatever the page size is, because it can no longer give you the little stuff you wanted, right? And most programs or most programmers are not aware of this difference, right? How many of you, when you do allocation, worry about the page size? How many of you thought of the page size concept? How many of you are taught about page size and all those things, right? You shouldn't have been, because most people you don't want to think about it. From a program, you just want to say, I only want 1 byte, I want to ask 1 byte, right? So since we decided that all of this will be in page sizes, your malloc really is a library call, and it goes to your own C library, which will ask the memory in page sizes and give it to you in little bit chunks, right? So even if you do malloc of 10 1 bytes, you only get 1 page, right? In fact, the malloc library may ask a really big chunk and then start to manage this stuff, right? If you want to see this, try doing this. If you, at least in Unix, you can do a top, and in Windows, you can do the task manager. Write a small program which keep asking 1 byte, right? And you'll see a program memory that is being used will be constant for a long time. Then it'll kind of jump to this one like this, and then it'll keep jumping, right? The amount of memory that your program uses will jump like this, right? It won't do like this. It won't do that. Even if it did while if you had a while 1 malloc 1, you kind of expect the amount of memory allocated to your process to kind of go linearly, right? You can't, because since you're doing paging, this program will be catastrophic, right? Because you keep getting pages. This is the worst case you can imagine, because internal fragmentation would kill you. So malloc library would request a certain chunk, so that's why it keeps changing, right? You may not have thought about all this stuff right now, but when you start to do programs for a living, you kind of worry about these things, right? Because you want to be aware of what the page size is, and you may want to work with the page size for some of the more performance-intensive stuff, right? Yes?
Sorry, kind of a random question, but when you malloc, does that guarantee that that data that you're asking for, or I mean the space you're asking for, is outside what your program is already in?
What do you mean by outside?
I mean, like, so it would be, so if you ask for a malloc, it would always not be in the same space as the program itself.
You mean the text, right? The actual program?
Yeah.
Yes. It usually, it won't be.
Okay.
I mean, it can't be, because usually when you ask for text, this is given as a text segment, so this is not modifiable, right? The program is in a different memory. I mean, it's considered to be a different memory, right? So the logical address given to your this will not be reassigned to something else, right? So when you start your program, you say, I want something for my program, right? My C program or assembly language program. So that segment will be called a text segment. Then you ask for a read write and a read only. So this is another read write memory that you'll ask, right? You rarely do you give back what you have and reassign it, because it's a lot easier for your program to exit and then get rid of this, right? Because very few cases do you do this, right? Very few cases do you not need some program memory that you already loaded, right? Does that make sense? But if for the bold, you can actually take a program malloc memory and then run it, right? Because C lets you run any memory location, so you can actually do this. You can run this, right? You can allocate a memory location and then load something in, and then you can run that, right? But that's C for you, right? You don't want to think about it, because that's a really yucky code. Self-modifying code is not something that you want to encourage, right? So anyway, so that's the deal. So you have this issue of, do I give it in one long chunk? So if I give it in small chunks, I get an internal fragmentation, right? But on the other hand, if you wrote a program where the segments are fairly large, that may be a good thing, right? So the pathological case of asking a lot of small segments, if all the programs tend to only ask for, let's say, 2 segments, right, which are really big, then the contiguous allocation may not be such a bad idea, right? But in general purpose operating systems, you don't want to depend on what the compiler can ask, so we went with paging, right? And I'm going to show how paging works. The next slide, so the idea here is, we want to have contiguous allocation. You as a programmer through your compiler ask for a large segment. So I'm going to give this large segment to you, but internally I'm going to allocate them into small fixed size chunks, right? We're going to call the fixed size chunks frames when you call it in the physical address space, and then pages when you call it in the logical address space, just so that we know what we're talking about. So if you say this hardware can support a frame size of 8K, right? So that's the frame size that the memory management unit will know. And from operating system perspective, you want to deal with pages. From your program, you deal with pages. They are the same size, but the page size is decided by the frame size supported by the hardware, right? Because we'll see in a little bit why the translation has to be 1-to-1, because otherwise it makes life harder. So once we do that, we have all you have to keep track is a set of free frames. And if you want something, I'm going to give you in frames. I don't have to worry about what size you ask for. So to find a space, the space allocation policy is trivial, because I need to find some free frame, not specifically anything. It can be anywhere, because since we have the logical to physical translation, I can allocate it to anywhere. So in the logical address space, it may be contiguous. Physical address space, it does not have to be, and there's no way you would ever know that, right? The way we do that is to have a notion called a page table, right? And which will do the translation from what you want and what the hardware wants. So the way we generate the page table is we take the address space, and since the frame numbers are in multiples of 2, right? We can kind of partition the address space into a page number and an offset, right? And we just do the translation of the page number from logical to physical, right? Before we go any further, you guys know hexadecimal math, binary math fairly well, right? Suppose we have 32-bit address, right? Which used to be the machine from a little bit back. Most of the machines now are going to 64-bit, right? Right. So this is right. So let's say you have a 32-bit address space, right? And suppose you have a 8K page size, right? So what is 8K? I'm sorry?
8192.
Yeah, so that's 13 bits, right? 13, right? Yeah, because 1K is 10, so 13 bits, right? So what this means is, if you take this address space, you take the 13 bits up, sorry. You take 13 bits out here, right? So if you logically ask for any page, right, this lower 13-bit will belong to within a particular page, right? Since I'm doing allocation on a page size, I don't have to worry about what happens with this address. I just have to translate this component from logical to physical, right? If I do that, I can translate any logical address to any physical address, right? I don't have to do this translation because since all the page numbers are the same size, right? This component will always be the same whether it's in the physical address or the logical address space. The only difference would effectively be here and here. And this is only true because all the frames are the same size, right? If the frames are different size, then it depends on the particular frame, particular memory you're looking for. But since you made all of them the same, this you don't have to translate. You only have to translate this from logical to physical, and it'll work out correctly. Does that make sense? Right? So essentially, the frame size comes in here. So the hardware decides what frame size it can support, and that frame size helps you define what this is. So now all you have to do is you have to have a table here called a page table, right? Where this is logical address, this is physical address. So if you ask for logical address 10, operating system has to maintain this notion of a page table, and let's say it says 20. That means a logical address of, let's say, this is 10, right? So this is 0x00, 0, 2. Is that right? So I'm trying to see if you have a logical address of 10, right? Which means that I'm looking for 0, 0, 0, 0, 0, 0, 0, 0. 10 is this will be the logical address of what I'm looking for, right? If I'm looking at logical address space of 10, that means this one I want to be 10, which is 0, 2, 4, 8. 8 plus 2 is 10, right? So this will be what I'm looking for. Actually, that probably is wrong, right? This is what it's looking for. So this is essentially 0, 0, 0. Sorry, this is 2. Let's say this 2, 8. Does that make sense? So I'm taking the address you have, right? From a logical address perspective, if you're asking for logical page 10, you are going to ask for 10 here in the top bits. The lower 13 bits you don't care. Let's assume they're zeros, right? That means the logical address you're asking for would have been this, right? In hexadecimal math. So if you have to translate this into page 20, right? So 20 would have been what? This is 20, right? 0x 0, 0, 0. Right? I seem to be losing people, right? Does that make sense? If I'm translating from a physical address of 10 to a logical address of 20, page of 20, I'm translating from this address to this address, right? But I don't have, so the easy way to do that is to just look at this component, right? And I'll get what I want, right? So essentially we're going to build this page table, what is called a page table. We're going to tell the operating system that for this particular process, I'm going to use this particular page table, right? I'm going to give the base, the size of the page table. And I'm going to say, if you want, you as a hardware, you can go whatever. And if you see any logical address that the user is asking, go into this table and look for the logical address and then translate that into a physical address space, right? To make it even simpler, I'm going to say, I'm going to get rid of the first component, right? I'm just going to make you go into this table and index it into the 10th item, and whatever you see there is what you want to look at, right? So go in here, look for the 10th item, and whatever the physical address here, go for it, right? So before you set up a process to run, you create this page table, you fill it with all the addresses that you know of, right, and make it point to something in your physical address, and then let it go, right? So what would happen if you didn't allocate some space? If there's some logical address which has no physical address mapping, it was never allocated to you, what would you put on the page table? We haven't told what it is, but what do you think should be there? So you are accessing a memory page in logical address space, which was never allocated to you, right? Which means that the operating system wouldn't have given you a physical address mapping, right? But the page table entry would still be there because you're depending on how big the space was, right? So what can you leave there? What do you think the operating system should leave there? A valid address or invalid address? Invalid. Yeah, you put invalid address, right? So let's say you put a -1 for some reason, right? So voila, now you have the other stuff you want, which is once I set this table up, I set the table to mark all the entries that I allocated to you. All the entries that I didn't allocate to you, I leave something illegal. So and then I let the hardware go. And the hardware, every time it tries to look at address, it gets a logical address, it goes to the page table, it figures out where the entry is, and if there's a valid marking, it replaces the logical address with the physical address, and off it goes. If there's an invalid one, you'll get a segmentation fault, right? And we'll see it more visually in the next slide. So, but essentially, that's the notion. You split the logical address into the displacement and the page number. And every time your CPU asks for a logical address over here, right, you split them into this P and D bits, right? And again, this is all done by the hardware. So US operating system has no control over how to split this P and D, right? That's decided by the hardware. So if you buy a hardware, it may say the D is 1K, 2K, 8K, or what have you. And then when you do the translation, you take that D bits as it is, because they don't have to change. For the other ones, you have this page table, right? And in order to avoid the second row and searching and stuff, you basically say, I go onto the pth location of this page table, and whatever was here, the hardware would replace it there, and then use that to access the memory page, right? So that translates to the physical memory, right? So this is how paging works. In this, the one which splits the P and D is decided by the hardware. The one which puts the F and D is decided by hardware. The notion that it looks into this page table and look for the pth element, that's decided by the hardware. What goes in here is decided by operating system, right? Hardware does not know what should be here. It's up to the operating system to fix this stuff, right? So if F happens to be here, it's moved up here, and then thing proceeds. If you have a negative value here, then or something illegal, you may get segmentation fault, right? So hardware has no way of, does not care what goes in here. It has to be told, I'm going to use a page table, right? The page table will start here and end here. Here's the page table. But you are free to modify what is in here. You as operating system is not free to define any of those. The P and D and all those things. Those are decided by the hardware, right? So if you have this kind of hardware mechanism, this is how you do the translation, and this is how the hardware and the operating system cooperate with each other. Make sense? Right? So thinking about a program, right? So let's say 32-bit operating system, and let's say we went with the 8K page size, right? Which means that 13 bits goes for the displacement bits. How big should this table be? it's a 32-bit address space, right? Which means that you can go from 0 to 2 power 31, right? That's 4 gig, right? So most of your laptops are most likely 32-bit machines. That means you can address up to 4 gigs of memory, right? And we said we're going to use 8K for page size, right? That's what your, let's say, hardware gives. That means you can, that's what, 2 power 13, right? So what's the, how many pages are there? It's 2 power 32 minus 13, right? What's 32 minus 13? 19. What is this? $19, right? 32 minus 13? 19, right? So what is 19? 2 power 20 is 1 meg, so it's 512. No, 2 power 20 is, yeah, 1 meg. What is 2 power 19? It's 512K, right? I think it's 512 because 2 power 20 is 1 meg, so it's 512, right? You know what this means, right? Your page table has to be 512K. 512K entries, right? And each entry has to be 19 bits, right? Because that's the translation you want. And traditionally, you give it like a 32 bits, right? So you're going to need this many words, right? Or in terms of bytes multiplied by 4, which is 2 megabytes, right? You're going to need 2 megabytes of page table size had you used an 8K page size on a 32-bit architecture. Does that make sense? In a 32-bit architecture, each process logical address space can be up to 0 to 2 power 31. So if you use a page table of size 8K, then essentially, if you do the math, right, you will have 2 power 19 pages. 2 power 19 pages is really 512K of physical addresses, which means that you would need 2 megabytes, right? So each process would need 2 megabytes of page table because page table is per process, not per operating system, right? So when you start a hello world program, I have to give you 2 megabytes of memory space, even though your program may be practically minuscule, even though the amount of space, even though most of the entries are going to be empty, your page table will have to be this big, right? What happens if you make the page size to be 1K, 2 power 10? If you make this 2 power 10, right, the number of pages will become 2 power 22, which is 4 mega words or 16 megabytes, right? So that's the challenge, right? If you have a large page size, right, you have lots of internal fragmentation, right? And if you have a lot of internal fragmentation, that's bad. But on the other hand, the page table will be small, right? If you have a small page size, then your internal fragmentation will be very small, but your page table size will go very big, right? And the larger the page table becomes, the more memory you need per process, right? To make matters even more interesting, the page table could either be swapped in or can be in memory, right? You could do the same thing we talked about before in terms of swapping. So the hardware can swap in and swap out the page tables, right? Would you want to swap in the page tables, or would you want to leave the page table alone? Where would you want to keep this page table? In the hard disk, in the main memory, or the fastest memory you can think of? Remember what happens every time you do a page. Let's go back to this stuff, right? For every machine instruction you do, right, I need to look at the page table to figure out what this happens, right? So if I were to page this out, if I were to swap this into hard disk, then your performance is going to be super awful, right? Because every time you do this translation, it has to be brought in. So you want this as close to your memory as possible. You want this right there, because otherwise this translation, so to access one memory location, now you have to access two memory locations, one for your page table and one for the actual memory, right? But if this happens to be in hard disk, then the whole thing is going to slow down, right? In the best case, when both of them are in memory, in the case where both of them are in the memory, you're going to double the amount of time it takes for you to access a memory. Now you have to access one memory, and you have to access the page table memory, and that could be a bad thing, right? So of course you have to solve this, and we'll see how we can solve that. But already we are adding. So the nice things about page table is operating system can set this up and let it go, right? We can't possibly put this in a cache because it's so big. I mean, it's like 16 megs or something. You can't put this in the cache, right? So now think of what happens when you new processors. Most of you may have 64-bit machines, right? All the machines on the lab is 64-bit, which means instead of 32 bits, there are 64 bits, right? Right? So how would the page table become in that case? We're not going to do the math. It's going to become very large, right? It's going to become so large that you can't store anything, right? If you do, you can do the math offline. But if you take 64-bit address space, it doesn't matter what your page is. It's like 8 or 10K or something. You're still going to have such a big memory, the page table, that the entire memory will be used up for the page table, right? We have to do something different for 64-bit. This works for 32-bit. It's easy to explain. 64-bit, the whole thing becomes more complicated. That's one of the reasons why you can't just go from 32 to 64. Because if you go from 32 to 64, what happens to the page table, right? Everything else is fine. Page table is your final boundary, right? If you go the other way, it's easier, right? If you go to 16-bit, things are a lot easier. So back then, they used to complain about how big the page table was. But now we are kind of okay, because a couple of megs per page per process is fine. So this is the translation which is happening, and hope you understand what's really going on, right? And why you can split that, do this math. And this is the reason why you want to keep them in multiples of 2, right? If you make the page size not a multiple of 2, then this translation cannot be done so easily. If it's a multiple of 2, then I can kind of chop off a little bit set of bits and then do some for displacement, other bits for the page table, right? So when you do the architecture class, this is one of the things you probably went through in more detail, right? How this translation happens. All this happens in hardware. Things are fast. And so one more, like little more examples, right? So in the logical memory, if you had this page 0, 1, 2, and 3, right? The operating system creates this page table, tells it to the hardware that for this process, I'm going to use this page table, right? It's going to start from there to here. And so the first entry happens to be 1. The next entry happens to be 4. Third entry happens to be 3. And 4 happens to be 7. That means on the physical address space, right, the page 0 happens to be on frame 1. And page 1 happens to be on frame 4. Page 2 happens to be on page 2, and page 3 happens to be on frame 7, right? So operating system can decide to move pages around such that they can put the page wherever it wants. It has to make sure the page table is updated, right? But once you do this, from your program perspective, the whole segment is contiguous. You get all these addresses in contiguously. Whereas in physical address, it may be non-contiguous. It may be wherever. There's no notion of external fragmentation here. There's only internal fragmentation, which we don't care about. As OS, we don't care about because we only allocate in page sizes. We ignore internal fragmentation, right? So in terms of if you have if you store strings, like for example ABCD all the way through, I just store them in the memory location. So on the physical memory, it may be non-contiguous, right? A, B, C, D, E, F, G, H is there, and then it kind of goes off somewhere. From a program perspective, everything looks contiguous. From a physical address space, they may be wherever they want, right? And the nice thing is, the next time operating system can decide to put you into the swap this page out, this frame out, bring it back later. Let's say move it here, And if it happens to be here, all it has to do is change that table entry to the right one, and your program will notice no difference. It'll keep working fine. Right? And now it also makes the whole, so if you, in terms of allocation, right, you have to keep a list of free frames. So operating system only has to keep track of this one table called free frame list. And then once it allocated your pages to you, it all goes to the new page, and the free frames happens to be only one left, right? So operating system has to keep track of only one data structure called frame list. So it has to figure out which frames are allocated, which is not allocated. And if you ask for something, I'm only giving you in frames. So the allocation policy becomes easy, right? So this whole scheme makes the whole process simpler. Not necessarily the best way to go depending on your scenario. But this makes life a lot easier because operating system only has to keep track of these few tables, set a few tables up, and then off you go, right? And anything happens, it gets notified. And we'll see what we can do with these tricks. So we can do a lot of tricks by changing the way these page tables are set up. But essentially, this will achieve the goal of translating from physical to logical to physical address space and doing these operations. And I'll talk a little bit about this before we can probably repeat it in the next class. Like I mentioned before, the page table has to be large, right? The page table becomes larger depending on what the frame size is. So it has to be kept in main memory, because otherwise things are going to be extremely slow, because every address will have to now take twice as much time, right? So we solve this problem by using a notion called TLB, right, which is a hardware concept, using a concept called associative memory, right? And how many of you have hardware background on associative memory? Actually, it's a computer science concept, right? How many of you heard of associative memory before? A few of you, okay. Associative memory is, you might see it in programming language like Lisp, right? Essentially, the idea here is it's like a search, except it's done all in one step, right? The idea here is you have a table, sort of what you have, page number and the frame number. When you do associative lookup, right, I store page number on the first column and the page number on the second column. And if I ask for page number 4, if it's associative memory, then in one cycle, I'll get the answer whether it's there, and if it is, what the answer is. If it is not, what it's not, right? If you don't have associative memory, you do a sequential search, you do a bubble sort or whatever. So you kind of search from the top, and you maintain a certain way, you search in a certain way. If you have associative memory, I can ask it, do you have it? The answer is yes or no in one step, right? And this is a hardware feature that is implemented. So essentially tells me upfront whether it has in cache or not, right? And I'm going to show you this graph, and we can get back to this graph. So essentially what I'm trying to optimize here is I added this notion of a TLB. TLB is associative memory. It's very expensive. It takes a lot of chip size, so you have to make it as small as possible because of the hardware cost reasons. So you have a certain amount of TLB entries here. So if you buy a new processor, it tells you how much TLB entries it has. But what it means is the hardware itself keeps track of, it's a cache for the page table, right? If you reach the same page table entry over and over again, it keeps this mapping of page to frame in the TLB cache, managed entirely by the hardware. What it does is, if you ask for a new page, it looks up on the TLB in parallel to actually looking up here. If it finds it in the TLB, it would have done a match. It would get you what the frame number is, and then it will cancel this operation. If not, it will go through the memory address, right? We'll see it again in the next class. But essentially, this is a way to improve the performance. This is done entirely by the hardware. Operating system has no input on that one, right? But the software, if it is aware of this stuff, you may get better performance programming it a certain way and not programming it another way. And we'll see how that is in the next class, right? So again, this is more of what the modern processors are even more complicated than this one, but this is how you get somewhat of a decent performance. So I guess we're out of time. So we'll meet again on Wednesday. If you have any questions, let me know, especially with this whole binary arithmetic and stuff. Right?